This might be our last video, Fluid Mechanics 8, so last on fluid mechanics maybe. And in this video I will look at just a few questions related to the Bernoulli's equation and the ability of the airplane to lift itself and fly. So let's look at some of the questions. At any given time there are 4 forces acting upon a craft. These forces are lift, weight or the force of gravity, drag, and thrust. Lift is the key aerodynamic force that keeps objects in the air. It is the force that opposes the weight, and lift helps to keep an aircraft in the air. So the weight is the force that works vertically by pulling all the objects, including aircraft, toward the center of Earth. And in order to fly an aircraft, a force like lift is needed to press in the opposite direction against the gravity. So the weight of an object controls how strong the pressure or lift will be needed. And lift is part like the pressure, that the change of the pressure between the top and the bottom. And drag is the mechanical force that generates by the interaction of with the air resistance. So let's look at the image of the picture that we have here. So I have the cross-sectional area of the wing, and on the top you see there's like longer distance to travel, and on the bottom there's shorter distance to travel. So the air on the top flows faster than the air on the bottom. So the wing is designed to help the air on the top to flow faster than the air on the bottom. And I have good videos for you that has a more detailed explanation on how the wing works. Like Minute Physics has a very good video, and then I think a few more I posted for you in our lessons. So here in the picture again, you see the air on the top is going to be floating faster than the air on the bottom, because the air on the bottom is slower, then it has more pressure on the bottom than on the top, and that extra pressure from the bottom lifts the airplane. And by using Bernoulli's formula, we look at the wing and the airplane to be in the same level. So you have rho gh part of the Bernoulli's formula disappearing in this equation. There's no need to keep rho gh because the height of the airplane on the whole level is the same. And the change of the pressure between the bottom and the top is going to be the difference of their kinetic part of the formula, where you have 1/2 rho v top squared minus 1/2 rho v bottom squared. And so let's look at the questions that we can use this formula to solve problems. I only have a few questions for you to solve in this area. So let's look. An airplane is flying at an altitude of 1,000 meters above the ground. The density of the air is 1.123 kilogram meter cubic per meter cubic, and the velocity of the air on the top of the wing is 60 meters per second, and the velocity on the bottom of the wing is 30 meters per second. And the pressure on the top of the wing is given. So this part is also given, the top of the wing. We'll find the pressure on the bottom of the wing. So from Bernoulli's formula, I have the pressure on the top plus 1/2 rho the velocity on the top squared is equal to the pressure on the bottom plus 1/2 rho the velocity at the bottom squared. So I'm looking for the pressure at the bottom. So the pressure at the bottom is going to be equal to the pressure on the top plus 1/2 rho, if I factor it out when I move them all to the same side, and the velocity at the top squared minus the velocity at the bottom squared. So if I plug in my numbers, I have the pressure on the top is 88,600 plus 1/2. The density of the air at this height is 1.123. The velocity on the top is 60 squared minus 30 squared, the velocity at the bottom. And that will give me the pressure at the bottom equals to 90,116 this question, they say that 15 meter per second wind is blowing across the roof of your house, and the density of the air is given 1.29 kilogram per meter cubic. Determine the difference of the pressure caused by the air inside the house and the air outside of the house. Because the air inside and outside of the house almost at the same height, I can cancel the potential part of the Bernoulli equation, and again I have P1, or I can say the P1 plus 1/2 rho, and then I have V1 squared is equal to P2 plus 1/2 rho V2 squared. And they ask you to determine the difference between them, so all I have to do is, so if this is inside of the house and this is outside of the house, then the difference is P1 minus P2 is equal to, or change of the pressure, is equal to 1/2, and then I have rho V2 squared minus V1 squared. So the velocity outside of the house is V2, and that's 15 meters per second, but there's no velocity inside of the house, so that is 0. So that gives me 1/2 rho times V2 squared, because V1 is equal to 0. So the change of the pressure between the inside of the house and outside of the house is equal to 1/2, and then the density of the air is 1.29, and the velocity is 15 squared. So that will give me 145 Pascal. So I have 145 Pascal is the difference between the top and the bottom pressure inside and outside of the house. In this question, they say an airplane has an effective wing surface of 16 meters squared that is generating the lift force in level flight. The air speed over the top of the wing is 62 meters per second, while the air speed beneath the wing is 54 meters per second. What is the weight of the plane? So if this is cross-sectional area of the plane, then I have the forces, the mg, and the force of the lift. I'm gonna call it with the L, force of the lift, mg. And the net force is equal to 0 because the airplane is not going up or down. So, and I have the velocity on the top of the wing is 62 meters per second, and the velocity at the bottom of the wing is 54 meters per second. So I can calculate the force of the lift, which is the same as force of the airplane, by using Bernoulli's equation. So I'm gonna say P1, or P top, plus 1/2. The density, velocity on the top squared, is equal to P bottom plus 1/2. The density of the air and the velocity at the bottom squared. And the density of the air, we just did in the previous question, air is 1.29 kilogram per meter cubic. So now I have the change, or the difference of the pressure between the bottom and the top is equal to 1/2 the density of the air and the velocity on the top squared minus the velocity at the bottom squared. Just the same as we did in the previous question. So the pressure is equal to 1/2 the density, and then the velocity on the top is 62 squared, and the velocity on the bottom is 54 squared. So that gives me the change of the pressure between the top and the bottom is equal to 598.56 Pascal. And to find the force, so I know the pressure is equal to the change of the force between the top and the bottom over the area. So the difference of the force between the top and the bottom is equal to the change of the pressure times the area. So that gives me 598.56 times in the area they give you. So 56 times the area is 16 meters squared. And this will give me 9,577 newtons. So the lift force is equal to 9,577 newtons. So the weight of the airplane is equal to 9,577 newtons. And in this last problem in this video, we're gonna look at the problem that involves the graph. Every time I have students do the problem with the graphs, they usually get confused just by seeing the graph, or they get scared seeing the graph. But usually the problems with the graphs are not as difficult as the other ones that we have been solving in our classroom. So suppose the plane problem above, the one that we just did earlier, is now flying at an altitude of 500 meters. And this is one of the first questions we did. What is the pressure difference between the top and the bottom of the wing, assuming that the pressure on the top is still 88,600 Pascal? Use the graph that they give you to estimate the air density at the new altitude. So the altitude is given the horizontal line. So the horizontal line is the altitude. And it is flying at 500 meters. So 500 meters is here, right there. And that looks like the density is 1.17 at 500 meters. So I have the density and I have the altitude line. So this is the altitude line, this is the density line. So the density changed. And all they ask in this question is use the graph to determine the density at the new altitude. So all you have to do is to determine the density at the new altitude, which is 1.17 kilogram per meter cubic. And that will be it for our fluid mechanics video 8 for now, where we did some problems involved airplane and the lift and the weight of the airplanes. And thank you for watching, and I'll see you in the next video.